Recording in progress.
Okay, good morning, everyone. And we start now. So we have finally got to this point. That is, we can summarize and illustrate all what we have discussed so far about the Pareto optimal. We break down the Pareto optimal in 3 levels. Exchange level, we call exchange optimal, and the production level, we call this technical efficiency or production optimal. And then we bring together consumption, we call exchange, and production. We bring together the 2 aspects of a social and economic life. And we come up with the idea of the so-called top level. And now we summarize all what we have discussed so far into this general picture. And this is about our production technology. So by the way, let me double check. Every Friday is a bad day. Can you hear me? Is everything is okay today? Or give me quick feedback. Just drop me a couple of words from the chat. Okay, good. Thank you, Fanny. Okay, and so, this is about the production. So in reality, we start from this one. We train the resources, labor, capital, material, water, so on and so forth. Basically, we call labor and non-labor input. That's resources. We train resources into something we can consume. This is the production. And we can train all the resources into X or into Y. If we produce more Y, we have to decrease, we have to produce less X. This is the production possibility curve we call PPF. And then if we choose any point, that is technically efficient point, that is, we do not waste any resource. We organize our production very efficiently. We don't make any waste. And then suppose we are producing here, we are operating in our whole society from a core at this point. That means we produce this much for X and this much for Y. And then we focus on this given level for production, we can discuss the so-called exchange optimal. And we collect all the exchange optimal all together, we can draw a curve. Each point is exchange optimal. But in general, we have only one point such that we can get the so-called top level. Top level requires this one. This one, this is our golden equation. We organize production. At the same time, we organize exchange or consumption for everybody, you and me, for any individual I. And if we bring together the 2 numbers, they are equaling to each other, we get the so-called social optimal or top level optimal. And at that point, this number, this is marginal rate substitution for both Alice and Bob. They both equal to the marginal rate of transformation. So from this simple discussion about what may happen if we choose this social production at a society level, you can, in general, you can get some insight. That is, for a given level for production, we usually have one point, which is the top level optimal. But the point is, we can always choose another number different from this one. For example, we can choose this number, quite different from this one. Here we produce more X and then less Y. Here we produce more Y and then less X. And here, if we organize our social production at this point, and then we can also discuss what may happen in exchange for this given level, given plan for social production. Then again, we collect all such exchange optimal altogether. In general, we have only one point, which is global optimal or top level. Here, we sometimes we talk about the top level. Sometimes we call social optimal. Sometimes we suggest global optimal. That's the optimal. And so now, for some examples, then we can have by looking at some examples, we can have a much better understanding of how to put everything together into a picture like this. So that's what we are going to do today, and probably also part of time, maybe more than half of time next class. I think the examples are very, very useful and also very illustrative and can be used to illustrate the main points we have discussed. Some students keep complaining, all the discussing is so theoretical, it's difficult to understand. It's not very friendly. So today, let's make our class more friendly. And we look at some example. Let me find this one. And so now we look at two examples. One example is about this box. For giving social production, we have already done that. Then what's the exchange optimal? Another one, let's turn to the whole picture. We know some resources, for example, from Macro Society, and how to get this so-called top level optimal. We look at two examples. One is about the exchange optimal. And after we look at the two examples, you will find that it's usually much easier to find the top level optimal than to find the exchange optimal. Theoretically speaking, exchange optimal is only one part of the top level, but in practice, it's much easier to handle global optimal or top level optimal than handling the exchange optimal. And now let's look at the first example. This example is only about exchange. And here we have again two persons, Alice, the girl, and the boy, B. And this is the utility function. So here, before we move to the next line, you should, for this one, you should have some good understanding in economics about this kind of utility function. The idea is, let me emphasize. So this one tells us something about who the girl Alice is. Alice is such a person. She cares more about X as twice as she does about carrying Y. Okay, so if you fix this number, this is 1, you increase this number, that is Alice will get more and more utility by consuming some X. So in other words, if this number is larger than this number, that means for Alice, X is more important than Y. And in this example, it's as twice important as Y. And Bob is different. Bob is another person. in economic terms because he had quite a different preference. For Bob, Y is more important than X. Okay, so this is the economic way of understanding such utility function. So this is about the preference. And what's the endowment? How many X? We have this much X, this much Y. So the point is we have to divide the total number 100 apples between the girl and the boy, and it's the problem and the same problem. I think that we are asked two questions. One, what's the optimal? What's the exchange optimal solution? That is, if we put all such good solutions together, we get a set. We call this set is the Pareto set. For this exchange economy, this is exchange economy. Nothing to do with production, just about exchange or distribution, allocation for products between the members in the society. And another one, and in general, this set is pretty large. It's very, very many solutions. And if we introduce some social wave function, remember we discussed, we spent one class on the social wave function. Social wave function is about kind of a value judgment. Value system, that is who we care more about and compared to other people, which group of people we care, and more than caring some other groups in the society. So therefore, this is about sort of political philosophy. If you care much more about the working class, or if you care much more about the middle income people, or you care more about the ladies, you care about the males, and so on and so forth. So therefore, this is about how we value the importance of the different groups or different individuals in the society. So in this example, let's consider this one. This is kind of, best meet, the best meet social wave function. We give a kind of a weight, alpha. Alpha is a number between 0 and 1, and give another weight, 1 minus alpha, to Bob. So here, the intuition is if we increase alpha, at the same time, we must decrease 1 minus alpha. Then we care more and more about eddies. If alpha equals 0, for example, whatever the value for u is, this term automatically disappeared, vanished. So therefore, if we don't care about eddies at all, give 0 weight to eddies in the total evaluation of a social welfare, then you can intuitively understand then the solution should be giving nothing to Alice because she's nothing for this very strange society for such a social wave function. At the same time, if we increase alpha, and then we treat Alice more and more like somebody, and more treating Barbara as nobody, then we should give more and more both good X, Y to Alice. This is kind of intuition before we start with the mathematics. How to solve the problem? And we will show step by step. Okay, please ask any question you have when we move forward. And I want to make sure everybody can fully understand all the solutions step by step. And this is example 1. Before we go ahead in detail, let me share with you Okay, don't worry about the marks I just produced. And another example is example 2. This is the top level. We still have the same person, Alice and Bob, but we introduce production. At the same time, we introduce some resources. We have some labor. This is a very simple type of resources. We have only one kind of resource, labor, no capital, and to simplify our analysis. And for this one, again, we need to find the optimal Pareto optimal solution. And then we also have the same problem. That is, if we have some social wave function still the same, and then, sorry, this is the solution, not the question problem part. And let me try to figure out where is the question top level. Okay, probably I put it into another file. So never mind, I will bring that question back to this file. Okay, now let's continue our discussion about this one, the exchange optimal. And okay, this is right. And how to solve it? You know what happened at exchange optimal? One condition, my marginal rate substitution is the same as yours. That's the only condition for exchange optimal. And for the top level, we have several conditions, but for this one, we have only one condition. And now we need to calculate what's this for Alice and what's this for Bob. And this one is marginal rate substitution equals marginal utility of X over marginal utility of Y. So let me explain this one. And just make sure everybody fully understand this one. So this one, we get it, we calculate this one. What's this? This one equals for Alice marginal utility in goods X. This is the marginal utility for X, for Alice, divided by marginal utility or for goods Y. Okay, so this is just a definition. So therefore, for this one, marginal utility or for X, basically you consider this one, the first order derivative about XA. Clearly it's 2 over XA. We get this one. That's the numerator. And now for this one, this is to calculate first order derivative about YA. Clearly is equal to 1 over YA. That's this one. And then we reorganize this one and put it in some way which look nice. It's a double YA over XA. Okay, I believe basically everybody is comfortable with this one. And similarly, let's turn to, oh, sorry, this is the Bob. I should, there's a typo. Let's turn to Bob. For Bob, it's very similar. Marginal utility for X, this is 1 over XB. Marginal utility for Y, that's 2 over YB. We get this one. Again, we reorganize. And then by this optimal condition, the two numbers must be the same. This number equal to this number. And let's Okay, and so now we put them together, we get this one. This is the marginal rate substitution condition. And so here we have 4 variables. It's very annoying. And so here I still give you some explanation about the meaning for this one. All the non-negative, all such number satisfy equation 1, equation 2, and equation 3. This is the equation 1. That's about constraint on the total number of x. This is the total quantity for y on the constraint. And the constraint, this is the one constraint, this is another. This is of the condition. So therefore here, equation 3 is the central condition. It's the central, the most important condition. And equation 1 and 2, you know, this is just a kind of a technical constraint. That's what we have. And we put the 3 equations together. And also here, for this one, if we are making use for this equation to solve the problem, xa can't be 0, xb can't be 0. So therefore, we also needed to consider the so-called what may happen if xa equals 0. Let's firstly, we double check what happens if xa equals 0. Xa equals 0 means we give no x to Alice, okay? And we give nothing to Alice. So therefore, Alice's utility must be extremely small. If this one equals 0, this number equal to negative infinity, 负的无穷大. Okay, that's an extremely small number. And so therefore, we should also give ya 0. We give no x to Alice, no y to Alice. So what does that mean? That means we treat Bob as our king and Alice as nobody. So therefore, this number is Pareto optimal, because if we want to make things better, we have to take some x from Bob and give it to Alice, or take some y from Bob to Alice. That will make Bob worse off. Bob will be very unhappy. So therefore, by definition, that's Pareto optimal. Even though it's not fair, clearly it's not fair, but by definition, that's Pareto optimal. So therefore, and also similarly, if we give everything to Alice, that's also Pareto optimal. So therefore, here we do not allow xa or xb to be 0, but later you will find we do not need to worry about the corner solution. Such corner solution clearly are good solutions. And this one plus all the, you know, the so-called non-corner solution, we call it interior conditions, utility solution. All such solutions, all such non-negative numbers which satisfy this one, that's altogether that's Pareto solution. But this one is really ugly, okay? Quite difficult to understand. And now we generally, quite naturally, we want to know, we want to really understand how the solution looks. Okay, this is the key words. We want to understand how the curve looks. Is it beautiful, is it good looking, or really ugly? And now let's simplify the mathematics. We pre-run the math in order to get something we can see, we can graphically demonstrate, graphically show how the solution looks like. And now we reorganize this one. Why we focus on Alice consumption XA and YA. And then YB equals 100 minus YA. Okay, given the constraint, we have 100 for Y altogether. So therefore, Y minus the quantity given to Alice is to be received by Bob. And similarly, this one, XB equal 100 minus X. And now we have a little bit better formulation. Here we have only two variables, XA and YA. You know, what we have done? We have done this by using three equations. Using equation 1 to formulate XB as a function of XA. Equation 2 to formulate YB as a function for YA. Equation 3 to formulate the whole thing. So therefore, we have already used all the conditions. We can't make the formula even better. So now let's reorganize this one. We'll put it in such a way. This number times this number, times this number. That's 100 minus XA times YA equals this number times this number. Okay, so now we claim this is what we are looking for. All the conditions, all the Pareto solution are described by this equation. Again, this equation is quite difficult to understand. What's that? Let's make some discussion before we move forward mathematically. And clearly, if you let XA equal 0, this number equals 0, and this number becomes 100. So therefore, if this number equals 0, this number becomes 100, this is 4, that's 400 altogether, then YA must be equal to 0. Can you see it? So therefore, YA equals 0, this number equals 100. So this is a solution of equation 4. On the other hand, if we let XA equal 100, okay, we give all X to Alice. And then this number will be 0, okay, because Bob has no X. So if this number equals 0, this equals 100, then this number must be 0. 0 means YA equals 100. So therefore, if XA, let me write it down to help everybody understand. That's the kind of, if XA equal 100, this number will be 0, and this is 100, so therefore this number must be 0. So in other words, if we organize the exchange at optimal, the so-called exchange optimal, then if we give all the X to Alice, we must also give all the Y to Alice. Okay, so then we get this one. So therefore, the corner solution, remember, this is kind of corner. Corner solution means take some number at the maximal or minimal. Sorry, that's optimal. So here you can see we don't need to worry much about the corner solution here because we put XA in the denominator, XB in the denominator. So therefore, we have good reason to worry about the zero value of XA, XB. But once we put this equation in this way, all such mathematical problem disappear. Okay, never mind, don't worry about it. So therefore, the corner solution automatically become a special case of the general solution described by equation 4. So therefore, this is a very simple equation, but this simple equation can teach us something quite interesting about the solution. Okay, and let me double check. Anybody had a question about this one? Okay, if no, let's move forward. And now it's still very difficult to understand how the curve looks. How the curve really looks like. Let's organize. Eventually, we can draw this curve. And if you are very good at such math exercise, probably you have already figured out. But now let's explain how to get to the curve from this equation. We reorganize. We put this is 4xa, this is 1. We put them together, we get 3. Basically, we move this term from this side to this side, we get 3. At the same time, this one 400ya also move to the right, we get this one. This 100x, we get this one. So clearly, this one is equivalent to this one, quite the same. But what we can learn, what we can benefit from formulating equation 4 in this way, something really important. And here, I don't know how many of you are still familiar with such exercise. I believe many of you have done such exercise in high school for many times. Let's put this equation in some way that we can find the figure. We can figure out the graph, the curve. How to do that? Here, this is the focus on the first 2 terms, okay? Then what we can learn, we extract ya, put ya outside. What's inside? Triple xa minus 400. Again, we put 3 outside, then xa minus this number. This is something meaningful in understanding how the curve looks. And then here, because we have this number, we naturally also want to this term, put it into some way like this. So therefore, this with 100xa, 100x minus this number, but here we have a new term. This term is something new, 100 times minus this number. So therefore, we must make up this term also on this side, on the 0 side, we get this number. Okay, and then what can we see about it? So therefore, we formulate this one altogether. Here we have 3. So therefore, this one, okay, I forgot to give you another step. Just making sure everybody fully understand. So now we put this one in a way xa, sorry, let me, it's very hard. Xa minus 400, 1/3 of 400. Okay, We take this term outside. What's left is 3y, 3ya plus 100, right? And again, for this one, we put it as such 3ya minus sorry for my very ugly handwriting. It's difficult for me to write it on the computer. Okay, and we get this number. And why do we do that? And the reason is, once done that, we can have a much better understanding. And here we have 3. We divide by 3 on both left side and right side, right-hand side. And for this one, divided by 3, this number disappears. This number disappears. What's left? This number times this number. That's this. And on the right side, this is 400 and 100. And here this is 40,000 divided by 3 again, 3, this 9, this number. And now what does that mean? And oh, so hard. If you have any question, let me know. I can explain before you get confused. Okay, so we get this equation. This is what we are looking for. We claim this is kind of hyperbola. Hyperbola, so just in case some of you are not familiar. Oh, shit. 双曲线, okay. You know, basically, this number, if this is not xa minus something, just xa times ya equals something negative. That generally means giving this is xa, this is ya, then this curve, this hyperbola should have 2 branches, 2 parts. One part is in this region, another part in this region. If this number is positive, should be here and here. Okay, that's kind of a hyperbola. For this hyperbola, but here we have something slightly different because this xa minus ya, that's why we purposely put it as ya minus something rather than ya plus 1/3 for 100. Okay, what's that? That is, so this is the framework we have. This is x, this is y, and we have x, so we have 100x, we have 100y. So basically we focus on this box. This box is ID1. Oh, it's very hard. This is AdWords box. So we allocate 100x and 100y between Alice and Bob. Here is Alice. Here is Bob. And now, let's focus on how many of X we give it to Alice. And that is, let's focus on XA and YA. This is YA. Okay. And as mentioned earlier, we can give everything to Bob. Alice got nothing. Or we give everything to Alice, Bob receive nothing. So therefore, this point and this point, both good solution. And how the curve in between looks like? This number tell us. So sorry, this curve tell us. And if we change this framework from 0, 0 to this point, 400 over 3, and for this coordinate for the horizontal variable, and for the vertical variable, we also move this one to a new original point, to this point. This is minus or negative 100 over 3 here. So therefore, we shift all the framework altogether to a new point, and then we draw the curve. One curve is here, another curve is here, but this curve is not relevant. Okay, this we have another one. Oh, sorry, it's quite far away. We don't draw it because it's diametric. So for this curve should cover the whole space very far away. But what matters is only this part for us. What's inside the Edgeworth box. So this blue color curve is what we are looking for. And this one is the graphic illustration of this equation. Okay, that's how the so-called Pareto optimal for such exchange economy. Can you see it? So we eventually figure out the curve or the graph, the picture, and okay. Before I move forward, so we finally solve the first part. Find the exchange optimal, and we find it mathematically, and then we also graphically show how the curve looks, how the set looks. The set is not that bad. It's okay. Now let's move to the next problem. Do you have any question? Everything is okay, or okay, we are moving too slowly, probably for some of you. We get the set. The set is a very, very large set, so many solutions. And now let's introduce the social wave function. And as mentioned earlier, once we have a kind of a value judgment, who is more important than another, and how we, attach importance to every individual in the society, we usually have one solution. Here we have very many solutions, multiple solutions. Here we have a unique, we have only one solution. Now let's confirm this general insight, this general observation for this example. We solve the second problem. And for the second problem, how to solve it? And we introduce two methods. The first method is quite simple and easy to handle. The second method, we call this a silly one. That's a stupid method. What's the smart method? Let's look at this one. We just reformulate the social wave function. This is utility function of Alice by consuming XA and YA. Respectively for cos X and cos Y. This is the utility function for Bob. But here, we already formulate consumption by Bob as a function of consumption by Alice. And now we have two variables, XA and YA. Basically, how much for each good, each product, each consumption goods Alice consumed. Okay, so therefore, let's look at the first order condition about XA. We get this one. This one, it's easy to calculate. This one, double alpha over XA. Another XA is here. That's 1 minus. We should get this number minus here because this is minus this one and equal 0. Okay, but we directly put it as this number equals this number. And for YA, again, here is for Alice, is alpha over YA. Another one here is for Bob, is minus double y minus alpha over 100 minus y. So we get two equations. And then what can we do about it? For this one, we have only XA. So it's easy to find that the solution of XA should be this number. Okay. The idea is, and you don't need to really calculate, just look at this equation carefully enough, then you can directly write the solution. And this number times this number, that's 200 alpha, right? Minus double alpha XA, right? Equal 1 minus alpha XA, right? Then you just shift the whole term because here we have XA. We are interested in XA. Combine with this one. This minus become plus, negative become positive. Here 1 minus alpha plus double alpha. So therefore, this one become 1 plus alpha, right? So therefore, what X alpha equal to alpha over 1 minus alpha, 1 plus alpha and times 200. And similarly for this one, you can solve YA. So the idea is alpha times 100. So that's only term which doesn't contain YA. For YA part, alpha minus YA and shift to the right, and we have plus alpha, so therefore 2 minus single alpha times YA equals 100 alpha, so therefore YA equals this number. And similarly, this is the solution given to Alice. And we have 100x, so therefore 100 minus this number is how much X Bob will receive. And this 100 minus this number is how much Y Bob will receive. Okay, you just, for this one, this step is rather easy and much easier and simple. And what's interesting is, let's make some discussion about it. And what can we learn as economists about this solution? So the idea is when alpha increase, this number also increase because this is the increasing function for alpha. Okay. So for example, when alpha equals 0, this term equals 0. When alpha equals 1, this term becomes half. half times 200, that's 100. So therefore, when alpha equals 0, xa equals 0. When alpha equals 1, xa equals 100. And this quite similarly for ya. When alpha equals 0, this term disappears. When alpha equals 1, this one becomes 100. That is alpha. What's alpha? Alpha is how important Alice is. When we increase the value for alpha, basically we treat Alice, we is for the whole society. The whole society treats Alice more and more like a queen. She's the princess, okay? And we treat Alice as very important person, like a queen. And then treat her like as a real queen. That's a joke, and we call that a real queen, means she should have everything, okay? And Bob is completely useless. Bob is a complete, nobody when alpha equals 1. Alpha equals 1 means this term equals 0. Basically, when we count the social welfare, we simply don't count Bob at all. Bob doesn't matter. So therefore, when we increase alpha, basically we give more and more importance, more and more weight to Alice. So therefore, we should give more and more goods to Alice. So this number simply telling this story. It's quite intuitive. And if you look at the curve, this is the good solution, the whole curve altogether, sorry, this one. It's a very, very many number, but for giving alpha, we have only one solution. That's how much Alice should receive at optimal. And when alpha increase, that's the, the error. Where I carefully draw the error. When we increase alpha from 0, x equals 0, this one equals 0, this one equals 0, we are starting here, okay? We treat Bob as the real king, Alice as nobody. When we increase alpha, Alice becomes more and more important. So she will receive more and more until here, she becomes the real queen. She controls everything. Okay, so therefore, for different alpha, we have different solution. So this solution is quite intuitive, right? That's why we introduce such a software function in this way. So this way is very, very, a little bit childish, a little bit quite simple, but this one can help us understand something rather bigger. In the come back to reality, come back to the real society we live in, and who control how much depends on how important they are in the social welfare function. Social welfare function is very important. Social welfare function is kind of principle, philosophy, which shape the public policy. And okay, and so before we move to the next ugly solution, let's spend a little bit more time discussing, sorry, let me figure out. Let's give me a couple of minutes, let me clear out this. Okay, so let's discuss the general implication which we can draw from such a simple example. This social welfare function carries very rich information about the public policy makers, how the policy makers care about the different group of people. Okay, if Alice is the working class, Bob is high income or middle income class or capitalist. Then when we increase alpha, our society care more and about the working class. Then when we consider how to allocate the products, the social welfare, the policy, and then we should give more and more such products, such benefit to Addis. And when we change the number for alpha, then we change the allocation. But in general, coming back to reality, whenever we have some election, we are voting for somebody, and we believe that person is a good choice for us. For Alice, big alpha is a good number. For Bob, small alpha is a big number. And usually, the different candidate, they don't change alpha. Each candidate has some value for alpha. So therefore, when we change candidate, when we change the person who are going to lead the society, we are changing alpha. We are changing the social welfare. And so therefore, whenever we have election, we are voting for different social welfare function. And why that matter? Because by choosing different social welfare function, we will have different result for the society. That's why the people in reality are fighting so hard. Let me give you some example. One example taken from United States, another example taken from Taiwan. And in Macau, we also have election, but the election in Macau is not very intense. It's not very competitive. And also the local people don't take it very seriously as Taiwanese or as Americans. In the United States, each time, every 4 years, they change the president. I'm talking about the presidential election. And to choose a good candidate, to choose a good president, is very important for the 4 year. That's a long term for every family, every individual. For the 4 year term, performance, social welfare, everything. And because to choose a different person, for example, between Joe Biden and Donald Trump, is to choose a different value for alpha. And this is a very simple example. In reality, we usually have much more such values, alpha, beta, delta, gamma, so on and so forth. That depends on what topic you are focused on. You can talk about the culture, and one candidate is more open to the foreigners, and more foreign students can get much more opportunity to come to US to get some scholarship. And another number focus on probably the economic measures, how the single mother can receive the welfare benefit from the government. That will depend on how important that fact is. Basically, by choosing a different candidate, a different person to lead the states is to choose a different number. So that means a lot, really, really important. And so that's why in the United States, in almost every time, they spend billions of dollars on the fighting between different social welfare functions or different political philosophy. Basically, when we choose the person has a fixed number for alpha. You can't change it. It's very difficult once that person takes control of the power. What you can do, change the person. And then you can change the number for alpha. Okay. And also in Taiwan, the Taiwanese also joke, we are voting animals and so many elections. And also, Taiwan is much, much smaller, very, very tiny economy compared to the United States. But again, the Taiwan spent much, much resources, much, much money and time on the election, on the Taiwan region, they call the president. And, that's what they call, but for mainland Chinese government, they call this Taiwan region or Taiwan province. Whatever they call, the point is the Taiwanese people do spend a lot of time and resource on such election because they are choosing different alpha. That number matters a lot, but you can't change it. The citizens, they are not part of the decision-making body, decision makers. What they can do, they can choose who makes such a decision. They can choose the decision maker. To choose the decision maker is to choose the value for alpha. So therefore, this simple story can tell us a lot to understand why people keep fighting in the election. Because that's important, a very simple reason for your daily life. And then now, let me check what time. Okay. Okay, let's move to, this is the one solution. How to solve the so-called top level solution for such a given social wave function. That's one way to solve it. And here you can see when we solve this one, and we just solve it directly. We didn't make use of what we have got from the first step, We don't use this one because when you look at what we have achieved by taking this method, you find this our solution. This solution naturally tells us when you give alpha different value, XA and YA will change from 0 to 100. So therefore, this solution also generally tells us this what we get when we change alpha, we change the number, we change the point. Eventually, when alpha running through 0 to 1, the curve running through this part. This is the Pareto solution. So therefore, this method is very simple, but also make a lot of sense. And one natural byproduct is the Pareto set. And another solution is let's try to find a good number, XA and YA, from the Pareto set. We know we want to maximize this value, but at the same time, we know that the solution must be inside the Pareto set. So therefore, we can make a use of what we got from the first step, and then we solve the problem. This is how to do it. To solve this problem, we have, again, we formulate a social wave function as a function of consumption by Alice, XA and YA. And at the same time, we know this is the constraint. We must find it from this set. And how to do it? Here we have YA. We can put YA as function XA, and then we plug this number, this result, back into this one. YA becomes this one, pretty ugly. And 100 minus A becomes this one, again, pretty ugly. And then you simplify this formula and you get this. This one is not that horrible, but it's still quite complicated. And you find the first order condition. Here we have only one single variable, XA, right? And then you calculate the first order derivative about XA this number triple alpha over XA, this number is triple 1 minus alpha. Here is minus. The denominator becomes 100 minus XA. And this one again, and then you have to be very careful in organizing this one. And here, after certain, just manipulate this mass, then you eventually get this one. And this one, this term doesn't matter because XA can never be as big as 200 because we have only 100 altogether for X. So therefore, this term is never equal to 0. We get this one we get XA equal this one. And then once you get XA, you also get YA and so on and so forth. Look, you can see this method is okay, but unnecessarily stupid. Okay, it's too complicated. And if it's complicated, you can easily make a lot of mistakes. I do, you do, everybody does. You know, this is such a long process. You just keep annoying, really annoying. And when you do it, you don't enjoy the calculation. You just suffer. And if you suffer, you make a mistake. That's quite natural. And we are not a superman, superwomen. We're just normal. Okay, so this is another way to solve it. But we call that don't do it. That's silly. That's not an efficient way. So that's one example. Probably we are almost running for time. And perhaps I should not go to the next example today. We spend the next class on the top level optimal example. And you know, we spend the whole class just going through this simple example step by step. I think our effort today will pay off because it's useful to explain how to solve a problem step by step. And also because what we have done will be very useful for solving second problem. Okay, before I think we should not go to the second example. And let's come back to try to make sure everybody understand. You know, we didn't make use of very many pages that for today's class, but I just want to make sure everybody understand the detail, the solution. Any question? You can either type by or just ask. Just use the microphone and ask question, or in Chinese or in English, doesn't matter. Do you have any question to ask? Or do you find that you know, we spend much time, make a lot of effort, eventually we find the solution? Do you find that the solution is quite intuitive, right? It's quite sensible. It's if you look at the curve, this is the solution for the first one. We figure out this one, this part, this fragment of the curve is what we are looking for. That's a so-called exchange optimal. And then for the second one, we have even better, more lovely result. Basically, this is what we get. Depending on the value for alpha, we are running through the whole curve. I think this solution is quite sensible, quite intuitive. And also what's interesting is, if you look at more carefully, when alpha increase, this one increase at the very beginning. I think this number is 200. This one number is 100. And yeah, when alpha is small, I think this number is bigger. And when alpha is larger and larger, probably this one is bigger. Okay, any question? No, everything is okay? Okay, and if no question, that's end for today. Okay, and let me check. So the optimal XAYSB is giving, sorry, what do you mean optimal? Sorry, I don't quite understand. Karen, can you explain? Just hi, can just use the microphone to ask, okay? You ask, so the optimal XA is given to one of the person. What do you mean by that? So XAYA, XAX, the first question answered, okay. Let me, I think you are asked this one. So the optimal, the exchange optimal, you ask the meaning of XAYA, or you ask how the whole curve looks. The meaning of XAYA is at exchange optimal, how much X and how much Y is given to eddies. XB and YB is how much for each X and Y given to Bob. Okay, and the whole curve, we can move. The whole curve, this one, each point along this curve is one exchange optimal solution. And each point, for example, at this point, we give this much, of X to Alice, this much of Y to Alice. At the same time, this much of X to Bob, this much of Y to Bob. So this is one such good solution. So therefore, this is a curve. Along the curve, we can take any point. Each point is a good solution. Okay, but the point is, at such point, each such point, we can't make things better, and so therefore we have very many solutions. But when we introduce the social wave function, that's another criterion. Then the solution shrink to one point, depend on the value of alpha. Hi, Karen, are you okay now, or did I answer your question, or because I'm not quite sure what you precisely ask? It's okay? So any other question? Okay, we are ready for time. If no, so that's all for today. Okay. Okay, bye-bye. Take care. See you next Tuesday. And that will be our. Okay, thank you. You too. It's also student day, not only teachers day. Okay, I'm joking. Okay, thank you. Okay, bye-bye. Take care. I will sign off. Okay, bye-bye. Stop everything.